Assalamualaikum warahmatullahi ta'ala wabarakatuh, and very good day to whom is my concern. Alhamdulillah, we meet again in this video today. I do hope you all be happy and healthy every day. This video is made to continue our lecture on the subject MEC451 Thermodynamics. Please note that this video is best viewed with reference to the lecture note provided. Also, please note that this subject is for you ITM student for the program EM220 Bachelor of Engineering Honours Mechanical and EM221 Bachelor of Mechanical Engineering Manufacturing Honours. However, I do welcome everyone who would like to watch this video to open his or her knowledge of the thermodynamics. This is a lecture on Chapter 3, Part 4. And for this video, I will explain about the energy balance for an open system with a steady flow system. Previously, in Chapter 3, Part 3, we have discussed about the application of the energy balance equation on the closed system. Note that the closed system does not allow the mass goes into the system. Thus, the term mass flow in the right side of the energy balance equation is not applicable, and leaving the energy balance equation of the closed system as Q in plus work in minus Q out plus work out is equal to the change of internal energy, the change of kinetic energy, the change of potential energy, or we can rearrange in as a Q in minus Q out plus work in minus work out is equal to delta U, delta KE, and delta PE. On this video, we will discuss about the energy balance equation for the open system. Please note that for an open system, all three components of the left side of the energy transfer are applicable. Therefore, the energy balance equation for the open system is slightly different from the closed system. Okay, let us proceed into our main topic. As I explained earlier, this topic is discussed about the application of the energy balance equation for an open system. However, for this course, we will limit our discussion just up to a steady flow system only. Therefore, we will not cover the unsteady flow system. Basically, steady flow process is defined as a process during which a fluid flow through a controlled volume steadily. The fluid properties in the system basically can change from point within the controlled volume. However, at any point, they must remain constant during the entire process. Referring to the figure given in this slide, that open system consists of two inlet and one outlet. The inlet on the left-hand side of the system only allow 2 kg of the fluid to flow through it, and the right-hand side will only allow 3 kg per second of the fluid that can pass through it. In another word, the mass enter into particular inlet must remain unchanged. Therefore, the flow is set steady since the mass flow rate for each inlet is remain constant. Steady flow only considered at particular inlet. Therefore, although in this system we have two inlets with different mass flow rate, the steady flow only consider each inlet. So, I do hope that you all do not get confused about this. Another terminology that we need to define here is a control volume. This is because, as I defined the steady flow process earlier as a process during which a fluid flow through a control volume steadily, the control volume means the size of the volume of or the size of the boundary of the system is unchanged or remain constant or fixed size. It is similar to what we have learned earlier as a rigid tank. It is called control volume because the volume of the fluid must always occupy the volume of the tank. Combining the definition of the steady flow process, which is the mass flow rate at any particular inlet, to an open system must remain constant, together with the definition of the control volume that the volume must be fixed. Then we can define what we call as the mass balance for a steady flow system. Since the mass flow rate at the inlet is constant, as well as the volume must remain unchanged, then the mass flow rate at the inlet must equal to the mass flow rate at the exit of the system. Or we can write it as m.1 is equal to m.2. This equation is known as the mass balance equation. Normally, in this study, state 1 is referred to the inlet and state 2 or higher number of the states is referred to the exit of the system. Please note that for an open system, the mass must flow into the system and flow out of the system. Therefore, we will use the mass flow rate with the symbol of m dot, where its unit is kilogram per second instead of m in the unit of kilogram. Actually, the mass flow rate can be determined by using the equation of density time velocity and time the cross-section area of the fluid flow as shown in this figure. So, when we substitute this equation into the equation of the mass balance, then we can get density at state number 1 multiplied by velocity at state number 1 multiplied by cross-sectional area at number 1 must equal to the velocity at state number 2 times density at state number 2 and cross-sectional area of the exit system. So, this equation is specifically for the single inlet and single outlet of the open system for a steady flow process. However, if we have multiple inlet to the system as well as multiple outlet of the system, then we can write this we can write the mass balance equation as summation of the mass at the inlet is equal to summation of the mass at the outlet of the system. Okay, during a steady flow process, the mass flow rate at the inlet and at the outlet of the system is remain unchanged. Moreover, the volume of the mass within the system or inside the boundary also must remain unchanged. Then, the total energy content of the control volume must remain constant. Therefore, it will give the effect on the condition of the change in the total energy of the control volume must equal to 0. Referring to the basic equation of the energy balance equation, then all components on the right-hand side of the equation, which are the change of the internal energy plus the change of kinetic energy and the change of potential energy is equal to 0. Therefore, the amount of energy entering a control volume in all form, which is in the form of heat, in the form of work, and also in the form of mass flow, must equal to the amount of energy leaving it, so that the general energy balance equation for a steady flow system can be written in the red color as energy dot in the form of heat, work, and mass flow is equal to the rate of energy leaving out of the system in the form of heat, work, and the mass flow only. Okay. Before we proceed to the energy balance for an open system under the condition of control volume, let us first discuss about the third mechanism of energy transfer, which is by the mass flow. In general, the approximation of the steady flow process can be illustrated as in this figure. So this figure is basically illustrate the steady flow process, or we call it as a schematic diagram for a steady flow process. If we refer on that figure, we can make an analogy of the piston at the inlet and at the outlet of the system to simulate the mass flow in and out of the system. So we can use this is as a piston cylinder device. Okay, so this is at the inlet and this is also piston cylinder device at the outlet. Therefore, in order to make the mass flow in and out of the system, we need to push the piston by giving a force to the inlet of the system. Therefore, the piston will move forward. Remember that the force acting through a distance is the work done of the piston. Therefore, that work is known as the work required to push the mass into or out of the control volume. This work is necessary for maintaining a continuous flow through a control volume. Okay. Knowing that force is equal to pressure times area, then when we substitute this equation into equation of the workflow, which is workflow is equal to force times distance. So our force is P times A. Then now we can get the workflow is equal to P times A times L. Then we can rearrange this equation since A times L area times distance is equal to volume, then our workflow is equal to pressure times volume in the unit of kilojoule. Or we can use it as a specific workflow is equal to pressure times specific volume. So we will get the specific workflow is equal to kilojoule per kilogram. The workflow, which is PV, is actually the energy required for maintaining a continuous flow through a controlled volume. As I point out earlier, that every substance must have its own internal energy. Therefore, the fluid flow must also have its internal energy. Next, when the work energy is applied on the fluid will flow. Note that the fluid also have a mass. Then the mass is a flow. It will have its own velocity. Thus, it will create what we call the kinetic energy of the flow. Furthermore, if the fluid flow from the inlet and outlet of the system involve the different height, then the gravity will take effect to form a potential energy of the fluid flow. Therefore, the specific energy of the flowing fluid can be written as internal energy plus kinetics energy plus potential energy. Or we can convert into their formula. So we have internal energy. So we have velocity, power of 2 divided by 2. This is basically a kinetic energy. And then we can get what we call the last part is the potential energy by gravity times the different height. Thus, the specific energy transport by mass of the flowing fluid, or we denoted it as theta. So, theta is the symbol for the mass flow, is the summation of the work required to push the mass flow, okay, or the workflow. And the specific energy equation can be written as theta is equal to PV plus E. So PV plus U plus KE plus PE. We know that based on enthalpy, okay, H is equal to U plus PV. Then we can rearrange this equation. Finally, what we can get is mass flow is equal to enthalpy plus kinetics energy and plus potential energy. Or, okay, we can write it as H plus velocity power of 2 divided by 2 and plus Gz. Basically, this is what we call the energy transport by mass flow. Based on the previous equation, we understand that the energy transport by mass is taken care by the enthalpy. In fact, this is the main reason for defining the property of the enthalpy. Therefore, the equation of the energy balance for a steady flow system can be written as Q dot in plus work dot in plus summation at the inlet of the mass flow rate times theta, which is the energy for the mass flow, is equal to Q dot out plus work dot out plus summation at the outlet m dot times theta. After that, we can adding all the element, which is the heat, the work, and the mass flow into this equation. So, the energy balance can be written as Q dot in plus work dot in plus summation or at the inlet of the mass time the enthalpy time the velocity power of 2 divided by 2 time Gz is equal to Q dot out plus work dot out plus summation of the mass at the outlet time enthalpy at the outlet velocity at the outlet divided by 2 plus Gz at the outlet. This is the complete equation of the energy balance for a steady flow process. Okay, now let us apply this equation into several into several steady flow engineering devices. Okay, so what you have to understand is this is basically the final equation of the energy balance for the open system under the case of control volume. Basically, many engineering devices operate essentially under the same condition for a very long period of time. That means this device will run continuously without stopping for a very long time. For an example, the component of steam power plant, which are turbine, compressor, heat exchanger, and pumps, will operate non-stop for a month or even a year before the system is shutting down for a maintenance. Therefore, this device can be conveniently analyzed as a steady flow devices, so that we need to use the energy balance equation for a steady flow system in analyzing those type of the device. For this course, we will cover 9 primary steady flow engineering device as follow. So number 1 are nozzle, followed by diffuser, turbine, compressor, pump, throttling valve, mixing chamber, heat exchanger and condenser, as well as combustion chamber and boiler. What it means is we have to use what we call our energy balance equation that we have derived before into this 9 steady flow engineering device. So that let us go one by one. In this slide, we will discuss about the nozzle and diffuser. Basically, nozzle and diffuser are commonly utilized in the jet engine, in the rocket, in the spacecraft, and even in the garden hoses. A nozzle is defined as a device that increases the velocity of the fluid by reducing the pressure of the fluid. The simplest example of the nozzle is the garden hoses. The top figure aside is illustrate the schematic diagram of the nozzle. As we can see on that diagram, the cross-section area at the inlet is way bigger than the cross-section area at the outlet of the nozzle. This geometry will allow the velocity at the outlet is way higher than the velocity at the inlet. Note that the velocity of the fluid flow will give an effect on the kinetic energy of the fluid flow. Therefore, we can say that the nozzle is a device that used to increase the velocity and kinetic energy of the fluid flow. Okay, next, let us see about the diffuser. Basically, the diffuser is technically defined as a device that increases the pressure of the fluid flow by slowing it down. So, the simplest example of the diffuser is the speaker. So, remember, when we use the speaker, our voice will become louder. Actually, the working principle of the diffuser is opposite than nozzle. As you can see the schematic diagram of the diffuser on the bottom side of the figure. So this is basically the schematic diagram of the diffuser, which is opposite than nozzle. So the cross-section area at the inlet of the nozzle is way smaller than the cross-section area at the outlet of the nozzle. Therefore, the inlet velocity of the nozzle is the inlet velocity of the diffuser is much higher than the inlet velocity at the outlet of the diffuser. In another word, the kinetic energy at the inlet of the nozzle of the diffuser is higher than the kinetic energy at the outlet of the diffuser. Okay, so that is the introduction for the nozzle and diffuser. Okay, now let us go for the analysis. In order to do the analysis on the nozzle and the diffuser, first we have to make some assumption in order to reduce the complexity of the analysis. Okay, in general, we assume that the heat transfer from the fluid flow to the surrounding is very small and can be neglected. Okay. Next, the nozzle and diffuser does not involve any work. So the work on the nozzle and diffuser is equal to 0. And finally, we assume that the potential energy is equal to 0. So this is basically due to the nozzle and diffuser is always arranged in a horizontal streamlined fluid flow. Okay, all right. So, and the other one is the effect of potential energy is normally very, very small as compared to the value of enthalpy. That's why normally we neglect the effect of potential energy. Okay then. Based on the energy balance equation for steady flow process, which is Q dot in plus work dot in plus summation of mass flow in is equal to Q dot out plus work dot out plus summation mass flow out. Okay, all right, that we have derived earlier. And by considering the assumption that we have made before, so our assumption is basically we don't have the Q in, we don't have the work in, we don't have the potential energy, as well as we don't have work out, Q out, we don't have work out, and we don't have potential energy at the outlet. So what left is, so the general equation for the energy balance equation for both diffuser and nozzle are this equation we see, which is H in plus velocity in power of 2 divided by 2000 is equal to H out plus velocity at the outlet power of 2 divided by 2000. So in general, this box show how the unit conversion is made in order to convert this kinetic energy into 2000. Basically, H normally in the unit of kilojoule per kilogram, but velocity power of 2 divided by 2 is basically joule per kilogram. So we need to divide it by 2000 in order to make the unit for the kinetic energy in the unit of kilojoule per kilogram. Okay, this is the sample problem 314 to demonstrate to you the way to apply the energy balance for a steady flow process for the nozzle. Okay, let us read the question together. Okay, the first one is said that steam. Okay, steam, please remember this is our substance and steam we refer to water. At 0.4 megapascal, this is pressure, 300 degrees Celsius, this is temperature, enters an adiabatic nozzle. Please do remember that adiabatic means heat transfer Q is equal to 0. With a low velocity and leave at 0.2 megapascal with a quality of 90%. Okay, what we have understand here is, so leaf means state number 2 with a quality of 90%. 90% quality mean the steam is in the mixture region. Okay, so that's mean x2 is equal to 0.9. So the question asks us to find the exit velocity of the nozzle. Okay, as usual, in order to solve this problem, so we have to record all the given data. So probably the best way to do it is by state by state. So in this slide, I already arranged it. At state number 1, we have P1 is equal to 0.4 megapascal. T1 is equal to 300 degrees Celsius and velocity 1 is equal to 0. Why this is equal to 0? Because in the question it said that with a low velocity. So thus, when the nozzle is said that low velocity, that velocity we can assume as a 0. Okay, so now we go for state number 2. The data that we have at state number 2 is the first one. We have pressure at state number 2, which is 0.2 megapascal. Okay, if you can see the data, state number 1, the pressure is 0.4 megapascal. At state number 2, the pressure is 0.2 megapascal. This is what we call according to the definition of the nozzle, which is to increase the velocity by reducing the pressure. Okay, next what we have for the state number 2 is x2 is equal to 0.9, and we are asking to determine the exit velocity. Okay, so based on the energy balance equation that we have derived in the previous slide, we do have the general equation for the what we call nozzle. Basically, okay, we can assume the Q, you not assume Q. It already give what we call Q is equal to 0, and nozzle will not do any work. And then we can assume the potential energy is neglected. Then we have H1 plus kinetics energy is equal to H2 plus kinetics energy at state number 2. We already know that V1 is equal to 0. So what we have, our equation is equal to H1 is equal to H2 plus V2 power of 2 divided by 2, or we can say this is divided by 2000. Okay, so now based on this equation, we don't know the value of H1 as well as we don't know the value of H2. So that, okay, so we have to determine the value of H1 and value of H2 based on the state. Okay, now we go to state number 1. So as usual, this is water. We have to define the state first. Okay, P1 is equal to 0.4 megapascal. T1 is equal to 300 degrees Celsius. Okay, okay, please use your knowledge at the chapter 2, properties of pure substance, determine the phase. So therefore we have the phase of state number 1 is basically is in superheated. So based on table A6, we get that H1 is equal to 3067.1 kilojoule per kilogram. Okay, so now we already get the value of state number 1. Next, we go for state number 2. So the data that we have at state number 2 is pressure at state number 2 is equal to 0.2 megapascal, which is 200 kilopascal. Okay, and then x2 is equal to 0.9. Obviously, this is in the mixture state. So we know that in mixture, we have to use the equation in order to determine the property. Therefore, H2 is equal to HF plus X2HFG at the pressure of 0.2 megapascal. Based on this calculation, we get that H2 is equal to 2486.1 kilojoule per kilogram. So therefore, we already get value at H1 and value for H2. So based on this equation, okay, so we can rearrange for velocity number 2 is equal to velocity number 2 is equal to square root of 2 times H1 minus H2. So we can rearrange the what we call the unit here. 2 times 1000 is basically 2000. So when we make a calculation, we get the final velocity is equal to 1078 meter per second. So this is what we call the unit conversion in order to convert the unit of the velocity for the kinetics energy. So in this example, as you can see, so the first velocity at state number 1 is actually 0. So now the diffuser increase the velocity drastically from 0 into 1078 meter per second. So in order to understand the value, you may do the calculation to convert it into kilometer per hours to know what is actually the real velocity for this fluid flow in the nozzle. Okay, and this is the sample problem 315, which is used to demonstrate to you the way to apply the energy balance for a steady flow process for the diffuser. Okay, let us see the question. Alright, the question said that the first one, air. Okay, now our substance is air. Please do remember, in order to determine the properties of the air, we can use the ideal gas law, which is PV is equal to MRT, as well as we can use the relationship of the ideal gas between state 1 and state 2 based on the process. Okay. Air at 10 degrees Celsius, the temperature is 10 degrees Celsius. Again, when we use the air as the substance, we have to convert the unit of the temperature from degrees Celsius into the Kelvin. So next it said that 80 kilopascal. So this is the standard unit of the pressure. Enter the diffuser of a jet engine steadily. Okay, with a velocity of 200 meter per second. This is the standard unit of velocity, 200 meter per second. Okay, the inlet area of the diffuser is 0.4 meter square. The question gives us the inlet area, okay, alright, of 0.4 meter square. The air leave the diffuser is velocity very small. Again, when the velocity is very small, we can assume the velocity is equal to 0. Okay, as compared with the inlet velocity. So then the question asks us to determine, number one, the mass flow rate of the air. So mass flow rate of the air is equal to m dot. And the second one, the temperature of the air leaving the diffuser. Okay, alright, so let us go to the solution or the ways to solve this problem. Okay, as usual, the first one, we record what we call the given data to us. Okay, state by state. The first one, we go for state number 1. We have P1, the pressure is 80 kilopascal. T1 is equal to 10 degrees Celsius. Velocity 1 is equal to 200 meter per second. And finally, we have the cross-sectional area of the diffuser is equal to 0.4 meter square. Okay, based on the energy balance equation for the diffuser, okay, let's see. Alright, sorry. So we see the data at state number 2. So the velocity is equal to 0. That's all the data we have, what we call, for the state number 2. Okay, next we go for the energy balance for the diffuser. Okay, obviously the diffuser, so it didn't say about what we call heat, it didn't say about what we call potential energy. So what we can assume here is we can assume the heat and potential energy are neglected, and obviously the diffuser, we don't have any work done. Therefore, the equation for the energy balance for the diffuser is equal to H1 plus V1 power of 2 divided by 2 is equal to H2 plus V2 power of 2 divided by 2. However, in the data given, we said that the velocity is equal to 0. So then finally, we can get what we call the energy balance for the diffuser in this case is equal to H1 plus V1 power of 2 divided by 2 is equal to H2. So if we look at this equation, basically, so we do not know the data of the H1. So we only know the data of V1 and we do not know the data of H2. Obviously, in this equation, we have two unknown with one equation. We cannot solve it. So what we have to do is we have to determine what is the value of H1 and what is the value of H2. Okay, all right. The first one. So the question asks us to determine the mass flow rate. So basically, so we start calculating the value of specific volume 1 by using the ideal gas law is equal to R multiplied by T1 divided by P. So this is basically come from PV is equal to MRT. So specific volume is equal to volume divided by mass. That's why we get V1 is equal to RT1 over P1. So substitute all the required data. It said that R is equal to the substance is air. So by referring to our table, so R is equal to 0.287 kilojoule per kilogram Kelvin. And of course, we have to change the unit of temperature from 10 degrees Celsius into what we call Kelvin plus 273. So now we know the value of specific volume 1. So based on that, we can determine what is we can determine the mass flow rate by using the equation of mass flow rate is equal to 1 over V1. Please remember 1 over V1 is equal to 1 over specific volume 1. This is actually the density. So please remember that specific volume is kilogram per meter cube. Sorry, V1 is equal to meter cube per kilogram and density is kilogram per meter cube. So basically 1 inverse specific volume, we can get what we call the density multiplied by velocity at 1 multiplied by the area. So we do have the data for the velocity. So we do have the data for the area. So substitute this one 1 over 1.015 multiplied by 200 multiplied by 0.4. Then we can get the mass flow rate as 78.8 kilogram per second. So that is the first answer for the mass flow rate of the air. Okay, the second one. So in order to determine the temperature of the air, so how we are going to determine the temperature of the air? Basically, we have to understand that for the ideal gas, okay, so enthalpy is equal to CPT. So therefore, we can determine the temperature if we know the value of the enthalpy. Then, so we can use what we call this energy balance equation, okay, which is the H2. All right, so in order to determine the final temperature from this equation, basically we can rearrange in order to get H2. So this one. So we get H2 is equal to H1 plus V1 power of 2 divided by 2000. So divided by 2000 is basically in order to change the unit. So now, so we don't know what is the value of H1. So H1 can be determined by CPT. So we do know the value of T1. Then Cp of the air, so basically 1.005 kilojoule per kilogram Kelvin. So I already told you how to read the property table. Please use that knowledge. Time 10 plus 273, you get 283. Then H1, you get 284.42. So from this one, you can get substitute this value into this equation, then calculate it. We can get what we call the value of second enthalpy is equal to 304.42. Okay, so based on the value of enthalpy, we know that enthalpy is equal to CPT. We rearrange this equation for the T2. We get that T2 is equal to H2 divided by Cp. Substitute the value, we can get the value of temperature at state 2 is equal to 302.9 Kelvin. Okay, now you have to see what we call the real situation here. So basically, so if you see here, the nozzle will basically increase the value of temperature. So the initial temperature is actually 283 Kelvin, and the final temperature is basically 302.9 Kelvin. So this is the way we use the energy balance. So this is the energy balance, okay, for the diffuser in order to solve the problem of the diffuser. So what you have to understand, basically, you have to master what we call the second topic, which is the properties of pure substance. So if you compare this sample problem 315 and sample problem 314, so basically 314 we use water and this one we use air. So this is how we are going to manipulate what we call our knowledge in order to solve the thermodynamic problem. Okay, now we will discuss about the turbine and compressors. Basically, turbine is defined as a machine in which the kinetic energy of a moving fluid is converted into mechanical energy by causing the blade rotor to rotate. The moving fluid for a turbine may be water, or we call it as water turbine, or steam, we call it steam turbine, air, and we call it wind turbine, or combustible product of the fuel, or we call it as a jet. In general, the turbine can be used both compressible and incompressible fluid. As the fluid passes through the turbine, work is done against the blade, which are attached to the shaft. As a result, the shaft will rotate and the turbine will produce the work. Please remember that the turbine produces work output from the moving fluid passes through its turbine blade. The schematic diagram of the turbine is given on the bottom right of the figure in here. So this is basically the schematic diagram of the steam turbine. So as we can see, the fluid will flow inside here and the steam turbine will produce the work output, and finally the mass flow rate will come out from here. Okay, so this is what we call the steam turbine. Please do remember, steam turbine is converting the fluid flow from the inlet into the work output. Okay, so next we see what happened with the compressor. So the compressor, it is actually defined as a device that is used to increase the pressure of the compressible fluid. Please do remember, the turbine can be used for compressible and incompressible fluid. However, for the compressor, we can only use it for the compressible fluid. Thus, it requires the work supply to the compressor from the external sources through a rotating shaft such as an electric motor. So in another word, the compressor requires the power from outside or the work input in order to move the compressible fluid. Compressor could not be used for incompressible fluid, as I said earlier, because incompressible fluid cannot be compressed. Okay, thus its function basically is similar to the fan. So in this figure, basically illustrate the schematic diagram of the compressor. As you can see, the fluid will flow from downward when the work input is given to the compressor. Okay, so it will compress the compressible fluid and move outside. So therefore, so at the inlet, normally this is atmospheric pressure, or we call it as low pressure. Okay, and then this is what we call the high pressure, we call it P high. Okay, based on the schematic, if you compare between, okay, between the compressor and the turbine, you can see that the most importantly is the work. So for the compressor, so we require the work input, but for the turbine, we will produce the work output. So this is what we call the main distinguish between compressor and turbine. Okay, now, so we have to understand, so we have to make some what we call general assumption in order to reduce the complexity of the analysis later. So in general, we always assume that the compressor and turbine are well insulated, thus the heat transfer from compressor to the surrounding or from surrounding to the steam turbine are zero. So this is our assumption. Basically, we have what we call small amount of heat has been transferred, especially when we use the steam turbine. So as well as we assume that the potential energy and kinetic energy is equal to zero. So this is because the value is actually very small. We have the value of kinetic energy and potential energy, but they are very small as compared to the change of enthalpy. After we understand the assumption that we made for the turbine and compressor, thus applying this general assumption for the turbine and compressor. In general, our basic equation for the energy balance for the closed system is equal to this one, okay, which is consists of the heat, the work, and the mass flow at the inlet, and the heat and the work and the mass flow at the outlet. Okay, let us go one by one. Okay, for the what we call first one, we see the turbine first. We know that our assumption for the turbine basically, so we assume that heat is equal to zero. So now we do not need what we call the work input for the turbine. Okay, we can cancel out, and as well as we neglect the effect of kinetic and potential energy of the fluid flow. Okay, so Q out, okay, also we cancel out, but of course for the turbine, remember we do have what we call work output. That's what we want. So actually we want work output for the turbine. So next we can cancel out the kinetic energy and potential energy of the fluid flow. So the remaining component for the energy balance for the turbine is mass dot in times H1 or H in work dot out plus M dot out times H dot out. So basically, as I mentioned earlier, so for the turbine, we want the work out. So we can rearrange this equation as the work dot out, or the rate of work, or this is power, is equal to mass flow rate times H in minus H out. Or we can say that what we call the work power of turbine is equal to M dot times H1 minus H2. So basically this is the general equation for the turbine. Okay, now let us go for the compressor. Okay, we know that the function of compressor is to increase the fluid pressure by giving the work input to the system. So what happened to our energy balance equation is the first one, of course, we don't have what we call, we assume Q in is equal to 0, and we have to give the power to the system, to the compressor. That means the compressor is required the work input. Okay, next, we assume that the kinetics energy and potential energy is very small as compared to H. We can cancel out. Similarly, we don't have Q out here, so we don't have work out for the compressor, and the value of kinetic and potential energy is very small as compared to H. Thus, what we have is actually, so our energy balance for compressor is work dot in plus M dot in time H in is equal to M dot out multiplied by H out. Sorry. So this equation is basically, this one is H out. So we can rearrange this equation. So since we want the work input, we want to calculate the work input for the compressor. So the power input to the compressor or work dot in can be calculated by M dot time H out minus H in. So if we say that what we call state number 1 is for the input and then state number 2 for the output, we can write that the power of the compressor is equal to mass flow rate of the fluid times the H2 minus H1. So basically, this is what we call the equation related to the compressor. So now you have to see the differences between the compressor and the turbine. As you can see on this slide, for the turbine, what we want is we want the work output. So for the compressor, so we need to give the work input to the system. So this is the difference between these two components. Okay. Alright, so this is basically the general analysis for the turbine and compressor. This is sample problem 316 to discuss about the problem of the turbine. Okay, first let us read the question. Okay, the question said the power output of an adiabatic. So adiabatic means no heat transfer. That in Q is equal to 0 both for inlet and outlet. Steam. Okay, when we say the steam, so the substance is water. Okay, we have to determine the property based on the property table of table A4, table A5, and table A6. So this is actually the steam turbine. Okay, steam turbine is 5 megawatt. So the power output of the system, so power output of the system is equal to 5 megawatt. And it give what we call the data. Okay, so it said that the inlet pressure is 2 megapascal, inlet temperature is 400 degrees Celsius, and it have, interestingly, this question said it have velocity of 5 meter per second, and it have Z is equal to 10 meter. Okay, so therefore we cannot use what we call assumption here because the question already give the velocity and Z. So velocity will affect our kinetic energy, Z will affect our potential energy. So thus in our energy balance equation, we have to include this component later. So at the exit, the question said that, so we do have what we call the pressure of 15 kilopascal, and it said that X is equal to 90%. So that means state number 2, the substance exists in the mixture region. And then it said that velocity is 180 meter per second and Z is equal to 6 meter. So Z is basically determined from the similar datum. So that means Z1 and Z2 is determined from similar datum or similar reference point. So the question asks us, the first one is to compare the magnitude of delta H, delta KE, and delta PE. So basically, the question asks us what is H2 minus H1, what is KE1 minus KE2, sorry, KE2 minus KE1, and then what is PE2 minus PE1. Okay, then the question asks us to determine the work done per unit mass of the steam flowing through the turbine and calculate the mass flow rate of the steam. Okay, So let us go one by one. So whatever question, the first thing is we have to gather all the data, and the best way to do it, our data need to rearrange state by state. Okay, now we go for state number 1. So we do have that pressure 1 is equal to 2 megapascal. Temperature 1, we do have it at 400 degrees Celsius. Okay, please use your knowledge at the what we call second chapter, properties of pure substance. We have checked the what we call the boundary. Either we use PV diagram or TV diagram. So based on that diagram, we can get what we call our phase at the state number 1 is basically superheated. So when it is superheated, we can use what we call table A6 to determine what we call the value of H1 at pressure 2 megapascal and temperature 200 degrees Celsius. So this is basically just read directly from the table A6. So now we get H1 settled. Then we go for state number 2. So at state number 2, we get pressure is 15 kilopascal, and the data give to us X2 is equal to 0.9. So we know that the quality mass in the phase of what we call mixture. So from this one, we can calculate the value of H2 by using the equation of HF2 plus X2 HFG. So we put at the 15 kilopascal. Then we put all the data. We can get H2 is equal to 2361.73. Okay, so now we solve for delta H, delta KE, and delta PE. Okay, so the first one, H2 minus H1. So when we put the data, H2 is equal to 2361.73 minus H1 is equal to 3247. We get the value of negative 885.87. So this negative value is indicate that so the fluid is losing its energy. So why it is losing its energy? This is because that energy is converted into the rotating shaft of the work output. So that is mean by this negative value. So the fluid is transferring its energy into what we call the rotating shaft. Okay, that is the delta H. Next, we go for the delta KE. So delta KE similarly V2 power of 2 minus V1 power of 2 divided by 2000. So we get the value of 14.95. So in this case, the kinetic energy is gained. Sorry, the fluid is gain the kinetic energy. Alright, so basically the velocity at the outlet is much more faster than the velocity at the inlet, if you can see the value. Okay, so V2 is equal to 180 meter per second and V1 is 50 meter per second. Okay, so it increased basically 130 meter per second, but if you can see the value, it increased 130 meter per second, but it only increased the energy as much as 14.95 kilojoule per kilogram only. Okay, so now let us move on into the potential energy. As you can see, the potential energy, the formula is G Z2 minus Z1 divided by 1000. So this is just what we call to change the unit, and the fluid lost the potential energy as much as 0.04 kilojoule per kilogram. Okay, so it lost 0.04 kilogram. As you can see here, based on these three data, data of delta H, the data of delta KE, the data of delta PE. Based on these three data, you can see that the value of delta H is 885.87, regardless the negative. Negative mean that is losing the energy, but that is the magnitude of the energy 885 compared to the magnitude of delta KE is only 14.95, and especially data of the magnitude of potential energy is only 0.04. That's why we call the kinetic energy and the potential energy is much smaller than the change of enthalpy. That's why normally for the energy balance for the turbine and compressor, we always neglect the value of the kinetic energy and potential energy. Okay, all right, so this is example. This example actually to show to you how small what we call the value of kinetic energy and potential energy as compared to the enthalpy, and why we always neglect this value, which is the kinetic energy and potential energy. Okay, so the next question is said that determine the work done. Okay, the work done basically is come from the energy balance equation. So from our energy balance equation, so Q dot in we cancel out, work dot in we cancel out. Okay, so we have mass flow rate. Okay, and then so we do have H in. Okay, and now how about the velocity in power of 2 divided by 2, which is the kinetic energy? So we cannot cancel out because the question said it have the value. Okay, so we cannot cancel it. We can cancel it if the question don't say anything. So that is the purpose for the academic. So similarly for the potential energy. So what we can cancel out is basically the next one is we can cancel out the Q, okay, because this is adiabatic, and obviously for the turbine we want the power or work out, okay, and we cannot cancel out anything else. Okay, from this one, okay, it said that the work done per unit mass. The work done per unit mass mean in the unit of kilojoule. Work is kilojoule per unit mass per kilogram. Basically, this is the specific work. When specific work, we can neglect what we call the value of the mass flow rate. So we can change it as work out is equal to H1 minus H2 plus V1 power of 2 minus V2 power of 2 divided by 2000. This is what we call the change of kinetic energy. And finally, this is the change of potential energy. Please do remember that we already calculate what we call the change of enthalpy, so the change of kinetic energy as well as the change of potential energy. Then we substitute the value. Please do remember when we substitute the value, please do not change the sign convention. Okay, so when we change the sign convention, mathematically it will change our positive and negative, and we get different value. So if you can see in this figure, so in this solution, okay, the first one, all right, so check here, this is H1 minus H2, but our equation is H2 minus H1, so H1 minus H2, the value should be positive 885.87. So next, okay, V1 minus V2. Our equation is V2 minus V1. So this is positive 14.95. So when it is a V1 minus V2, it's become negative. So for the potential energy in this equation, Z1 minus Z2, we have here Z2 minus Z1 in terms of negative. So the value must be positive. So when we adding up everything, so the kinetic, the potential, as well as the change of enthalpy, what we got is we got what we call the value of the work done per unit mass is equal to 870.96 kilojoule per kilogram. Okay, this is how we are using what we call our energy balance equation in order to solve the equation, or specific problem. So interestingly, what you have to understand in this equation is, so basically you have to use every component we have in the energy balance equation, since we have the component of velocity and potential energy. Okay, so that's mean my advice is you cannot remember what we call the basic the final product of the equation for the turbine or the compressor, but you have to understand it from the energy balance equation. Okay, finally, so the final question asks us to calculate the mass flow rate of the steam. Then the mass flow rate, or m dot, can be calculated by the power divided by specific work done per unit mass. Please do remember that work dot out, the unit is kilojoule per kilogram, and work out is the unit of kilojoule per kilogram. Sorry, work dot out, the unit is kilojoule per second, and then work out is equal to kilojoule per kilogram. Then so if we divided this one, so this is 5,000, okay, kilojoule per second, which is kilowatt. So please be remember 5,000 is come from here, 5 megawatt. Okay, 5,000 kilojoule, okay, kilojoule per second time what we have work out is equal to, okay, kilojoule per kilogram. So basically kilogram per kilojoule. So you can cancel out kilojoule, kilojoule, and finally you will get the unit of kilogram per second, which is this unit is the unit of mass flow rate with the magnitude of 5.74. So this is how we do what we call the manipulating the equation in order to solve the particular problem of engineering device based on the energy balance equation. Okay, this is sample problem 317. The sample problem to demonstrate to you how we are going to use the energy balance equation for the compressor. Sorry. So let us read the question together. The first one, we say that air. So this is substance. Please recognize properly. So the data that we need to determine is basically we have to use ideal gas equation of law. PV is equal to MRT. Okay, it said that air is equal to at 100 kilopascal and 280 Kelvin. So this is pressure at state number 1. This is temperature at state number 1. Is compressed steadily to 600 kilopascal and 400 Kelvin. So this is pressure 2 and this is temperature 2. Okay, the mass flow rate of the air is 0.02 kilogram per second. And heat loss, please do remember. So this equation said we have the heat loss of 16 kilojoule per kilogram occur during the process. Assuming the change in kinetic and potential energies are negligible. Okay, so kinetic energy and potential energy are negligible. So then the question asks us to determine the necessary power input to the compressor. It said that we have to take the specific heat at room temperature. What does it mean is, when we say that specific heat at room temperature for our cases, in order to simplify the problem, so we use what we call 27 degree Celsius. So this is equal to 300 Kelvin. So from this one, when we refer to our property table, we can determine what is the value of R. Okay, so this is equal to 0.287 kilojoule per kilogram. And the other data, we need to use what we call the CP, specific heat at constant pressure. So this is equal to 1.005 kilojoule per kilogram Kelvin. And we have CV is equal to specific heat at constant volume. The magnitude is 0.718 kilojoule per kilogram, and the other one is equal to K. So K is equal to specific heat ratio, which is CP over CV. This is equal to 1.4. So this data you can refer to the table A2. Okay, so for the ideal gas equation of state and the properties of pure substance. Okay, so this is the data that we need when it said that take specific heat at room temperature. Okay, so now we go for the solution. So interestingly, okay, so this is what we call another way to solve the problem. We solve through what we call the energy balance equation. So based on our energy balance equation, so the question said this is compressor. Compressor, we don't have work output for the compressor. And it said that heat loss, so we already have Q out, but we don't have what we call Q in. Kinetic and potential energy are negligible. Okay, kinetic and potential energy are negligible, so that our equation is equal to power in is equal to m dot times H2 minus H1 plus Q out. Okay, capital Q, we can reduce it what we call to m dot multiplied by specific heat output. Okay, so because 16 kilojoule per kilogram, so this is what we call the specific heat output. Okay, so this is m dot, this is m dot. So basically, this one is equal to m dot, okay, times specific work. Okay, so if you want to determine the specific work only, so then we can cancel out m dot, m dot, m dot. So if you want to do that one. Okay, next what we have to do is we check the data, okay, for the state number 1. So we have P1 is equal to 100 kilopascal, T1 280 Kelvin. So we know that for the ideal gas, H1 is equal to CPT1. So when we calculate, CP is equal to 1.005. So this is as I mentioned earlier. Take specific heat at room temperature, refer to the table. Multiply by T1 is equal to 280 Kelvin. So we get what we call H1 is equal to 281.4. So now at the state number 2, we do have pressure 2 is equal to 600 kilopascal, T2 is equal to 400 Kelvin. Therefore, H2 is equal to CPT2. Then we get that H2 is equal to 1.005 times 400. And we can get the value of H2 is equal to 402 kilojoule per kilogram. Okay, with that data, basically we already complete H2, we have H1. So from this one, so we can calculate the power input because the question want the power, so the necessary power input to the compressor. So this is equal to 0.02. This is our mass flow rate is given in the question. So multiply by 402. This is H2 minus 281.4. This is H1 plus 16. So the answer is basically we get 2.732 kilowatt. So this is how, again, how we are going to use what we call energy balance equation. So now we have studied what we call 4 components. The first one is basically nozzle. The second one, diffuser. The third one is turbine. And the fourth one is compressor. Basically, all of these 4 components is based from the energy balance equation. So my suggestion is you cannot remember the equation for each particular device. What you have to do is understand the general energy balance equation, so which consists of heat, work, and mass flow at the inlet of the device equal to the heat, work, and the mass flow at the outlet of the device. Then from that, we have to understand what we call the assumption and the data given to us. From that one, we can develop what we call the equation for that particular problem. Hopefully, you can understand that one. In the previous slide, we discussed about the compressor. Recall that the compressor is a device used to increase the pressure of the incompressible fluid only by using external power source such as electrical motor. In this slide, we will discuss about the pump. Actually, the function of the pump is very similar to the compressor, except it is used for the incompressible fluid, or in another word, it is used to handle liquid instead of gases. General assumption for the pump are Q is equal to 0, which is it is well insulated. Delta PE is equal to 0, as well as the delta KE. Similarly, they are very small as compared to the delta H. So another assumption that we need to know about the pump, basically, due to the pump is used for incompressible fluid, that means the specific volume at the inlet is almost equal to the specific volume at the outlet. Thus, it will give to us that the internal energy at the inlet is almost similar to the internal energy at the outlet. Therefore, the energy balance equation for the pump is actually similar to the compressor, as the work pumped in is equal to m dot times H2 minus H1. From the equation of the work pump above, and by considering the assumption of specific volume 1, approximation to specific volume 2, and internal energy 1 is approximation to internal energy 2, then we can use, and also we can include that the enthalpy is equal to U plus PV. Then when we what we call divided the equation of the power of pump by m dot, we have the work pump in is equal to H2 minus H1. So H is equal to U plus PV. Then we can say that U plus P2V minus U plus P1V. Okay, this U, basically we know that our assumption U1 approximation to U2, so then we do not need to write it as U1 or U2. Similar to V1 is specific volume 1 is equal to specific volume 2, so then we do not need to write it as state number 1 or state number 2. So minus U plus P1V. Okay, so when we rearrange this equation, what we get is the work pump is equal to P2V minus P1V. Okay, we can cancel out the U, because U minus U. So then we can rearrange for this equation as the specific work input for the farm also can be determined as work pump in is equal to specific volume times the pressure difference. Okay, so this is another way how we are going to calculate the work pump. Please note that for our simplification, the state 1 is always assumed to be as saturated liquid. So normally this value of V we take as the specific volume at saturated liquid, or V is equal to Vf at given temperature. This is the sample problem 318. So basically, this sample problem is used to demonstrate to you the way to apply the energy balance equation for a steady flow processes of the pump. Okay, let us see the question. The question said a pump is used to draw a fresh water. Okay, please do remember the function of the pump is to increase the pressure of the incompressible fluid. So in our case, the incompressible fluid is the water. So it is used to pump the fresh water at 1 bar. Okay, so 1 bar, please remember this is equal to 100 kilopascal. and 30 degrees Celsius. So degrees Celsius with water, it meshed together. Do not need to change the unit to a 10 bar. So that means this pump is used to increase the water of the to increase the pressure of the water from 1 bar to 10 bar. So the question asks us to determine the required work input and enthalpy of the water after the pump. So require work input basically, will require work net, and the enthalpy is equal to H2 because this is after the pump. So in order to solve this problem, so we have to get what we call the given data to us. So the first one, we have the pressure is 1 bar 100 kilopascal, T1 is equal to 30 degrees Celsius, P2 is equal to 10 bar is equal to 10,000 kilopascal. So check the state. Obviously this is from the compressed liquid, so then we can use the approximation. So H1 is equal to HF at 30 degrees Celsius. Please do remember, when it is in the compressed liquid, we use what we call approximation method at a given temperature, not at a given pressure. So we get that H1 is equal to 125.74, and then we can get the V1 is equal to 0.001004. Similarly, V1 is approximation at VF at 30 degrees Celsius. So then the work input is similarly, we can calculate the work input. Work pump is equal to just the what we call specific volume time the what we call the pressure difference, P2 and P1. So in this case, we use what we call the value of specific volume of the value of V, specific volume at state number 1. This is because our assumption is specific volume at state number 1 is almost similar to the specific volume at state number 2 due to the incompressible process. So we substitute all the data. So V is equal to 0.001004. So P2 10,000 kilopascal. So this is 100 kilopascal. So what we get, the power of the pump is equal to 9.9396 kilojoule per kilogram. So this is what we call specific, work input. Specific work input. So then the enthalpy of the water, so we can determine the enthalpy of the water because we have two equations of the pump. The first equation is the earlier equation or the original equation. So basically the original equation is, so work pump is equal to H2 minus H1. This is the original equation. So after we make assumption of a specific volume is equal to specific volume 1 is equal to specific volume 2, and internal energy 1 is equal to internal energy 2, and also we know that H is equal to U plus PV, then we can get this equation. So now we have this equation, we can equate this equation. So or we can rearrange this equation is equal to work pump, then we can get H2 is equal to work pump plus H1. So we already get the value of H1, as 125.74. So substitute into the equation, we already get the work pump, so then we can get the H2 as 135.6796 kilojoule per kilogram. So this is what we call the way to use what we call energy balance equation for the pump. So but please remember, for the pump, what we want to use is what we call, we have to understand this equation or this relationship. Work pump is equal to specific volume multiplied by the pressure difference, also is equal to H2 minus H1. Then we can divide this equation into two parts, solve it one by one. So please do the practice for the pump, in order to master your knowledge of the energy balance equation. Now we will discuss about the throttling valve. Basically, the throttling valve is defined as any kind of flow restricting devices that cause a significant pressure drop in the fluid flow. The simplest example of the throttling valve that we are use every day is the adjustable water pipe valve as shown on the top figure aside. Another example of the throttling valve in engineering are the porous plug and a capillary tube. The main function of the throttling valve are to start the flow, to stop the flow, and also to regulate the flow of the fluid through any piping system. In order to regulate the flow, it means we have to control the mass flow rate of the fluid in the system. For an example, the water supply from our supplier, which is Sabas, is 30 kg per second, but we only want to use 0.5 kg per second for washing the plate. Then we can control it by using an adjustable valve as shown in figure A. When we want to control the flow, normally it involves a huge pressure drop. Note that the throttling can only reduce the pressure of the fluid flow but not increase it. That means the pressure of the fluid after the throttling valve must always lower than the pressure of the fluid before the throttling valve. We know that from chapter 2, the pressure and temperature is directly proportional. Thus, the pressure drop in the fluid flow is often accompanied by a large drop in temperature of the fluid flow. And for that reason, throttling devices are commonly used in refrigeration and air conditioning application. As for the analysis based on the energy balance for the steady flow process, the general assumption for throttling valve are the Q is equal to 0, it is well insulated. Delta PE is equal to delta KE is equal to 0. Also, this is because of very small as compared to delta H. Okay. Also, in throttling valve, we don't have any work. Hence, the energy balance equation for the throttling valve is, okay, the first one, Q is cancelled, no work. Kinetic energy is negligible, potential energy is negligible, Q out don't have negligible, so work out don't have, velocity kinetic energy don't have, potential energy don't have. So what is the remaining item for the what we call throttling valve is only H2 approximately H1. Considering that H is equal to U plus PV, then we can also write the energy balance for the throttling valve as U1 plus P1 V1 is equal to U2 plus P2 V2. So basically, this equation show that the internal energy plus the flow energy inside the system of piping after the throttling valve are constant. Okay, now let us see the application of this equation in the real situation or for the sample problem of the throttling valve. Okay, this is a sample problem 319. Basically, this sample problem is to demonstrate how we are going to use the energy balance equation in the case of throttling valve. Okay, as usual, the first one we have to read the question one by one. Okay, the question says steam. Okay, this is our substance. Steam is water. Enter a throttling valve at 8 megapascal and 300 degrees Celsius. Leave at a pressure of 900 kilopascal. Okay, that is what we call the statement of the problem. Next, it said that determine the final temperature. The question asks to determine the final temperature and specific volume of the steam. Okay, only 2 components. So in order to solve this problem, so obviously the first one we have to get what we call the given data. The first one is said that P1 is 8,000 kilopascal. 8 megapascal is 8,000 kilopascal. T1 is equal to 300 degrees Celsius. P2 is equal to 900 kilopascal. And the question asks us to determine what is the temperature at the exit of the throttling valve and what is the specific volume at the exit of the throttling valve. Okay, we go one by one. So the first one, we define state number 1, P1 8,000 kilopascal, T1 300 degrees Celsius. When we check our data at the table A4, we get that T1 is actually higher than T saturation at 800 kilopascal, which is equal to 295.01 degrees Celsius. Then state number 1 is in superheated region. So if the state number 1 at superheated region, then we can refer to table A6. Directly we can read the value of H1, 2786.5 kilojoule per kilogram. Okay, done state number 1. So now we proceed to the state number 2. Okay, at state number 2. Okay, state number 2, what we get is what we call P2 is equal to 2250 kilopascal. And we have to understand that H1 is equal to H2 in the case of throttling valve. Please do remember last time we already defined, okay, in the previous slide. So H1 is equal to H2 is equal to 2786.5. So what we get here is HF is equal to at 2250 kilopascal. So the value is equal to 936.21 kilojoule per kilogram, is smaller than H2, is smaller than Hg at 2250 kilopascal, which is 2800.5 kilojoule per kilogram. Then state 2 is in mixture region. So please refer to chapter 2, properties of pure substance, to really understand what does it mean by this component. Okay, so we know that it is in the mixture region. Then we have to determine the quality. So the quality is equal to H2 minus HF2 divided by Hg minus HF2. So from this one, put up all the data. So the data we can easily get from the property table. So now we can get X is equal to 0.9925. Okay, then we can determine what we call the specific volume. So state number 2 is basically is in what we call the mixture region. Then the final temperature is actually, so here T2 is equal to T saturation. Okay, T saturation at 2250 kPa. You can refer to the table for the real answer. Okay, alright, so next we can determine the specific volume at state number 2. So we have V2 is equal to VF2 plus X VFG2 at state number 2. So put all the data, put all the value, then we can get what we call the value of V2 is equal to 0.08806 meter cube per kilogram. So this is the way we are using the throttling valve. So basically the most important thing for the throttling valve is H1 is equal to H2. So this is what we call the identity of the throttling valve. The next engineering device under the category of the steady flow process is the mixing chamber. By definition, the mixing chamber is actually any section where the mixing process takes place. It does not have to be a distinct chamber. an ordinary T elbow or a Y elbow in our shower's room, for example, serve as the mixing chamber for the cool and hot water stream perfectly. For the mixing chambers, we need to do the analysis based on the conservation of mass principle, where for a mixing chambers, it requires that the sum of the incoming mass flow rate is equal to the mass flow rate of the outgoing mixture, or we can write it mathematically is summation of the inlet mass flow rate, so is equal to summation of the outlet mass flow rate. Okay. So if we refer to the figure of the hot and cool water shower aside, we can see that hot water, okay, goes into the system at one side and cool water enters the system from the other side. That means the system have two inlet. One is hot water, the other one is cool water. Moreover, both water is mixing together and regulate the temperature among them at the mixing chamber of this T elbow, so that the output water from this shower is only one, which the temperature is basically depend on the flow rate of the hot and the cool water. So that means it's depend on the ratio of the hot water and cool water. As for the analysis, okay, the general assumption that we always consider for the mixing chamber are, so the first one, Q is equal to 0 due to normally mixing chamber, we assume it is well insulated. Delta KE is equal to 0, so that delta KE, because of the value are very small as compared to the change of enthalpy. So, thus by considering what we call all other conditions above, and also we have to understand that there is no work involved in the what we call mixing chamber, so that the energy balance equation, the first term Q dot in we can cancel out, the second term work dot in we can cancel out, the third one, the kinetics energy we can cancel out, the fourth one, the potential energy also we can cancel out, and then the Q out also we can cancel, work we can cancel, and then this is potential kinetic energy, potential energy we can cancel. So what is remain is basically the summation of the mass flow rate time H at the inlet is equal to the summation of the outlet of the mass time H outlet. So basically this equation is relatively similar to the throttling valve, except the mixing chamber normally have multiple inlet or we have multiple outlet. Okay, please remember throttling valve only one inlet, one outlet, but mixing chamber we probably have many, okay, inlet and we have many outlet. So in general, so mixing chamber is depend on the mass flow rate and also the enthalpy. Okay, this is sample problem 320 to demonstrate how we are going to utilize the energy balance equation for the case of mixing chamber. Okay, let us read the question. Okay, it said that consider an ordinary shower where hot water, okay, our substance, the first one is water, okay, at 60 degrees Celsius is mixed with the cool water at 10 degrees Celsius. Both are a similar substance, both of them are water. So, but one is hot at 60 degrees Celsius and the other is cool at 10 degrees Celsius. If it is desired that the steady stream of the water of warm water at 45 degrees Celsius be supplied, determine the ratio of the mass flow rate of the hot to cool water. So the ratio of the mass flow rate to the hot, this is basically how much we have to put the hot water at 60 degrees Celsius with the cool water at 10 degrees Celsius in order to produce the water at 45 degrees Celsius. Okay, so the question also said we can assume the heat loss from the mixing chamber to be negligible and the mixing take place at the pressure of 150 kilopascal. So basically we do not need what we call, we do really not need what we call the value of the pressure, because this is hot water. Normally it is in the what we call the phase of compressed liquid. Then we take the data based on the temperature, not based on the temperature. However, let it be as it is. Okay, let's see our solution. So the first one, we have to what we call establish our equation. So based on what we call the basic principle of the energy balance, energy dot in minus energy dot out is equal to the change of energy of the system. However, this is an open system and control volume. So steady control volume, so the change of energy of the system is equal to 0. So then what we have is energy dot in is equal to energy dot out. Okay, so for the mass balance, okay, we have m dot 1 plus m dot 2 is equal to m dot 3. So this is because we have two inlet. So this is the first inlet, hot water. The second inlet is cool water. Okay, then from this one, we do what we call arrangement whatsoever, as what we do in previous slide for the analysis of the mixing chamber. What we get is m dot 1 H1 plus m dot 2 H2 is equal to m dot 3 H3. So from this one, we know that, okay, we know that based on the mass balance equation, M3 is equal to m dot 1 plus m dot 2, so that we can get our equation m1 dot multiplied by H1 is equal to m dot 2 H2 is equal to m dot 1 plus m dot 2 multiplied by H3. Sorry. So when we divide this equation by m2, okay, so we get y. Let y is equal to m1 is equal to divided by m2. So why we divide by m2? So in this case, m2 is equal to the cool water. Look at the question. The question one, the ratio of the mass flow rate of the hot to cool water. That means hot to cool water. Hot divided by cool. So that's why we divide this equation by m2. So we get y is equal to h1 plus h2 is equal to y plus 1 multiplied by h3. Okay, so we know that the saturation temperature of water at 150 kilopascal is 111.35 degrees Celsius. So all the water is basically in the saturated, in the compressed liquid form. So if the water in the what we call compressed liquid form, then we can use what we call approximation method. So H1 we can get is equal to HF at 60 degrees Celsius. So based on our property table, this is 251.18 from table A4. Similarly, from table A4, H2 is equal to HF at 10 degrees Celsius, 42.022, and H3 is equal to HF at 450 degrees Celsius. Sorry, at 45 degrees Celsius. Sorry, this is what we call typo error. It's supposed to be 45. Okay, is equal to 188.44 kilojoule per kilogram. So now we solve for y, because y is our ratio of mass flow rate of the hot over the mass flow rate of the cool. So we solve it. So we put all the value. Then we get the ratio is actually equal to 2.33. So this is the answer. So this is the ratio. So that means, sorry, 2.33 part of hot water plus 1 part of cool water at 10 degrees Celsius, you will get what we call the water at 45 degrees Celsius. So it said that the mass flow rate of the hot water must be 2.33 times the mass flow rate of the cool water for the mixture to live at 45 degrees Celsius. So basically, in mixing chamber, yeah, we just what we call to determine what we call this ratio. So ratio between hot to cool or something else. So normally, please do remember for the mixing chamber, we have what we call multiple exits, and we can have what we call multiple exit. So we have to do what we call the mass balance equation, which is mass balance equation is the summation of the mass at the inlet must equal to the summation of the mass at the outlet. In this slide, I will discuss about the heat exchanger. Heat exchanger are devices where two moving fluid streams exchange heat without mixing it. Figure aside illustrate the schematic diagram of a typical heat exchanger. As we can see on that figure, fluid A, which is in gray color, flow at high temperature flow in the pipe. At the same time, fluid B, that is in red color, at a lower temperature, enter into the system and flow across the pipe, which fluid A is flowing. Since the fluid A and fluid B have different in temperature, then based on the second law of thermodynamics, in natural processes, the energy will flow from high to a low degree. In this case, the higher energy in the fluid A will transfer naturally into the fluid B. The result are the temperature at the exit of the heat exchanger of fluid A will be reduced and the temperature at the exit of heat exchanger of fluid B will be increased. Heat exchanger are widely used in various industries and they are come in various designs such as radiator and cooling tower. The general assumption for the heat exchanger are Q is equal to 0. So normally the whole system are well insulated, as well as the delta PE and delta PE is equal to 0 due to their magnitude is very small as compared to the change of enthalpy. Also, in heat exchanger, there is no work involved since the process is occur naturally. Thus, the energy balance equation, so the system is well insulated, cancel Q in, there is not involved any work. Delta KE and delta PE are negligible, there is no Q out, there is no work out, there is no velocity, kinetic energy and potential energy. So thus, what left in the equation is we do have what we call summation of the mass at the inlet time the enthalpy is equal to summation of the mass at the exit of the system. Okay, alright, so time the enthalpy. Okay, in our case, let us refer to what we call our system that we give here. So we have two fluid, we have fluid A and we have fluid B. Then our equation can be expanded as mass A in times HA in plus MB in plus multiplied by HB in is equal to mass A out times HA out plus MB out times HB out. So this is the way we use what we call the energy balance for the heat exchanger. Please do remind what we call the heat exchanger is differ from what we call mixing chamber is normally heat exchanger has two different fluid. Okay, this is the sample problem 321. So the sample problem to illustrate how we are going to use the energy balance for the heat exchangers. Okay, so let us read the question. Okay, the question said liquid sodium. Okay, so this is new substance. We have learned in MEC451 three main substance. The first substance is water. The second substance is refrigerant. Water and refrigerant, basically we calculate by using the properties is referred to the property table. And the other one is what we call the ideal gas, where the property of the ideal gas is calculated by using the ideal gas equation of law PV is equal to mRT. Okay, let us go through first. I will explain later. Okay, liquid sodium flowing at 100 kilogram per second. Okay, so this is the mass flow rate of liquid sodium. Enters a heat exchanger at 450 degrees Celsius. Okay, and exit at 350 degrees Celsius. If you see this schematic diagram, so liquid sodium enter here and exit here. Okay, so now this is entered at 100 kilogram per second and temperature is 450 degrees Celsius and exit at 350 degrees Celsius. Okay, the question said the specific heat, okay, of the sodium is 1.25 kilojoule per kilogram degree Celsius. Okay, water enters 5 megapascal and 20 degrees Celsius. So the water is enter here. Okay, 5 megapascal, 20 degrees Celsius. So the question asks to calculate the minimum mass flux of the water so that the water does not completely vaporize. So here water, so what we don't want is this one is not completely vaporized. Not completely vaporized is at state G. Okay, remember we have what we call state F and state G. G is what we call when it's changed completely into gas. So it asks what we call, we have to neglect the pressure drop in the heat exchanger. Also calculate the rate of heat transfer. So this is what the question asks us to determine. Okay. Alright. So based on the energy balance equation, so we already simplify the energy balance equation. We have two substance now. The first substance is sodium. The second substance is water. Okay, so in this case what we can do is actually by using the previous equation that we have derived previously in the previous slide. So what we have is equal to mass flow rate of the sodium time the inlet of the sodium plus mass flow rate of the water plus inlet of the water is equal to mass flow rate of the sodium at exit time what we call enthalpy at the exit of the sodium plus mass flow rate of the water at H outlet of the water. So when we arrange this equation, we can calculate the what we call sodium based on what we call CP, specific heat and temperature, because it given us the specific heat. So we can use this one. So for that one, we check what we call the value one by one. So state 1 for water is in compressed liquid. So we get 88.61. Okay. So state number 2, we don't want it completely vaporized. So we assume at saturated vapor. So we get it 2794.2. So then we rearrange this equation to get the mass of flow rate of the water. Then we can determine the mass flow rate of the water is equal to 4.62 kilogram per second. Okay, so that is complete what we call the first one is the mass flux. So that what we call our mass flux. So similarly to the mass flow rate. The second one is basically we are going to calculate the rate of heat transfer. So heat transfer from sodium into the water. So this is just simply Q water is equal heat of the water okay, is equal to mass flow rate of the water times H2 water minus H1 water. Substitute all the data, so we can get the rate of heat transfer is equal to 12.5 megawatt. So this is how we using what we call energy balance equation for our heat exchanger. In this slide, we will discuss about the combustion chamber. A combustion chamber actually is that part of an internal combustion engine, or we know it as ICE, in which the fuel air is mixed and burned. The burning process is actually to convert the chemical energy in the form of the fuel into the heat energy, and finally it will convert into the rotating shaft. In general, it is an enclosed space in which combustion takes place. For an example, the diesel and petrol engine as well as the jet engine. As you can see on this slide, so this is what we call the combustion chamber for the jet engine, and this is the combustion chamber for the petrol engine. In order for the combustion to take place, it is required the fuel. Basically, any fuel consists of its own energy, or it is called the calorific value, or denoted as CHV in the unit of kilojoule per kilogram. The higher the energy content in the fuel will give the higher heat that will be released during the combustion process. Also, the combustion process requires the oxygen. Normally, we use oxygen in the atmospheric air because it is the easiest and cheapest source of the oxygen. So, combination of the fuel and oxygen in the combustion chamber at certain temperature will result the combustion process. That means each of fuel will be burned with the oxygen at certain temperature. Generally, after combustion process, the combustion gases will be produced such as carbon dioxide and water vapor as well as other gases. In addition, the combustion gases have high energy that can be used to drive the turbine to produce the work output. We will learn this on chapter 6 in the Brayton cycle. Okay, so this is what we call the diagram to show the process of the combustion. The first one, we require the fuel with the certain energy value, and we have the oxygen goes into the combustion chamber, and finally it will produce what we call the combustible gases. So now the rate of the heat energy generated from this combustion process, or we denote it as Q dot Cc, okay, in the combustion chamber can be written as the efficiency of the combustion chamber multiplied by the mass flow rate of the fuel multiplied by the energy content. Normally, the efficiency of the combustion chamber is given in the unit of percentage. The mass flow rate is in the unit of kilogram per second, and calorific value or heating value is in the unit of kilojoule per kilogram. This is will give what we call our heat generated from the combustion chamber in the unit of kilojoule per second or in the unit of kilowatt. Okay, in this slide, we will discuss about the boiler. In general, a boiler is actually a closed vessel or arrangement of vessel and tubes together with a furnace or other heat source, in which steam or other vapor is generated from water to drive turbine or engine, or to supply heat, or to process certain material or other purposes. Boiler can be divided into two types based on its arrangement. The first one is called the fire tube. Fire tube boiler is actually any boiler for generating steam by passing hot gases and other combustible products through tubes, or the fire is in the tube, immersed in water to a chimney or uptake. Top figure aside is illustrate of the fire tube boiler, where you can see at this one, this is the fire and this is the tube. The tube is immersed inside what we call the water. So this is the source of fire. So the water goes here. This is tube become hotter, and it goes outside. Okay. Then this is water. This water will absorb what we call the heat from this tube, and then it will produce steam at the output of the boiler. The second type of the boiler is the water tube boiler. It is actually a boiler for generating steam by passing water in the tube. So, which is opposite working principle as the first one of the fire tube. So, the water tube, okay, will have the water inside the tube that flow through flame and hot gases. So this bottom figure illustrate the water tube boiler. As you can see on the schematic diagram of the water tube boiler, the fuel and the air are fed into the boiler and combustion occur inside the boiler. So this is the boiler, what fire. So but this is water goes inside, and then this is inside the tube, this is a water. So therefore, the heat from the boiler is transferred into the water, and the water will change its phase from liquid into superheated at the end of the boiler. This superheated water will consist of high energy and normally will be directed into the steam turbine to produce the power from the steam turbine. We will discuss this steam power plant in detail in chapter 6 in the Rankine cycle. Based on that, we can calculate what we call the rate of heat energy generated, which is we denoted as Q dot B. So Q is heat, B is a boiler. Okay, by similar equation as the combustion chamber. So now the change is from the efficiency of combustion chamber. Now we use the efficiency of the boiler. Multiply by the mass flow rate of the fuel. Also multiply by the calorific value. The unit are the same or similar as the combustion chamber. So this is what we call the schematic diagram or simple diagram or process diagram of the boiler. We have what we call, this is what we call fluid goes into. So this is basically of the second type, which is the water tube boiler. So this is the fire. The fire need the fuel and air. So combustion occur in the red color. So the black color is basically the water. So this is what we call schematic diagram of the boiler, and this is the equation. The combustion chamber and boiler can be modeled as figure aside. So this is what we call the model of the combustion chamber, and this is modeled as the boiler. As you can see in that figure, both combustion chamber and boiler require fuel and air as an input parameter, and combustion will occur in the combustion chamber in the boiler. For analysis purposes, the combustion chamber and boiler involve no work, and for the perfect system, no heat loss. Moreover, the kinetic and potential energy of the mass flow also negligible. So, hence the energy balance equation can be written as, so Q in, we can cancel out, work in, we can cancel out. Okay, so the kinetic energy, potential energy also cancel out similarly at the output of the system. So that's what we have basically. Okay, so sorry, we do have what we call Q in for the combustion chamber. Otherwise, there is no heat input to the system. Sorry. So what we do have finally is we have Q dot in plus M mass flow in, H in, and H out. So from this one, we can rearrange. So we know that, so the system, the mass must be balanced. Mass in must equal to mass out. So we can get that the Q dot in is equal to M dot H dot out minus H in. Oh, and the other one, we have to understand that, okay, for the perfect system or ideal system, the amount of heat transferred into the system, which is Q dot in, is equal to the rate of heat energy generated by the combustion chamber and boiler. Thus, we can write it as Q dot in is equal to QCC is equal to Q boiler. So that means heat input to the system is equal to heat from the combustion chamber as well as heat from the boiler. Therefore, we have completed discuss about the combustion chamber and boiler. Okay. By completing the combustion chamber and boiler, we are actually completed the chapter 3, which is the first law of thermodynamics. As a conclusion to this chapter, we have to remember 4 important points. The first one is, the first law is derived from the conservation of energy principle, which is energy cannot be created nor destroyed, but it only can be transformed from one form to another. The second point from this chapter is, based on the principle, we can write it mathematically as energy in minus energy out is equal to the change of energy of the system. Please note that this is the only thermodynamic equation. This equation is also known as the energy balance equation. Based on this energy balance equation, we can apply it to the closed system and also to the open system within controlled volume condition. In order to apply the energy balance equation, we need to understand the assumption that we have been made to each particular device. So note that the student do not need to memorize all the equation for each devices, but only memorize the fundamental equation and understand the condition of the device or a problem. So basically, this is practice problem 3.3. This practice problem focuses on the application of the energy balance equation for the steady flow system. As you can see, so there are 6 questions in this slide. So this is another 1, 2, 3, 4, 5, 6, 7 question. Okay, for the practice problem 3.3, as we covered for the energy balance equation for the steady flow system. And finally, we have another question under the practice problem 3.3. So I do hope that you all complete the entire practice problem in order for you to understand this chapter properly. If you have any question regarding to this chapter, please ask in our WhatsApp group. Please note that we are going to use the knowledge from this chapter for the following chapter. Therefore, please try your best to understand this topic. By that, thank you very much and please stay safe.